Check, 1, 2, 1, 2. Welcome back, everyone. Please take your seats. We have an exciting Next to the Morning program. First up are Joanna White and John Daniel from the BFI, and they will be talking about preserving off-air TV using open source tools. Please take your seats because we are commencing as of now. Thank you.
Hello, I'm John Daniel, Digital Preservation Engineer at the BFI, the British Film Institute. Along with my colleague, Joanna White, we're going to talk to you today about the BFI's off-air TV recording system. The BFI National Archive began recording off-air TV to 1-inch tape in 1985. Selected programs were captured to tape by teams shown here who worked in shifts around the clock. Any sudden schedule changes or national events resulted in a flurry of last-minute recording activity on site. By 2008, we were recording directly to DV Store, allowing a more leisurely review periods. Today, the BFI is the body designated by Ofcom, the UK communications regulator, as the National Television Archive, under provisions of the Broadcasting Act 1990. This designation allows us to record, preserve, and make available TV off-air under Section 75, Recordings for Archival Purposes, of the Copyright Designs and Patents Act 1988, and later Copyrights and Rights Performance Regulations 2014 under Research, Education, Libraries and Archives. In 2015, off-air TV recording became an automated process, and this was made possible by BBC Redux. The BBC agreed to provide the BFI National Archive with a fork of their Redux off-air captured solution from their Research and Development Department. Created in 2007, by the time it reached the BFI, it was 8 years old. The BBC's Redux filled a whole room. The BFI worked with BBC developers to integrate it, with our digital preservation infrastructure, with the goal of storing MPEG TS files on LTO data tape and IBM TS1150 data tape in our Spectralogic tape libraries. Built on open source technology, Redux was written using Perl and C to run from open source Linux operating systems, and was highly celebrated for its innovative design and use of open source tools. With hardware development, ours just filled one rack. Since 2015, the BFI has captured and preserved 1.2 million programs. That's 953,000 hours or 39,000 days of television. If you fancy a challenge, you could spend the next 108 years catching up on all the off-air TV recordings from the last 7 years. This material included live television, sporting events, breaking news, and advertisements. The BBC stopped using Redux in May of this year. It's now end of life, and for a few years the BFI have experienced unreliability with our recordings. Increasingly, programs can be recorded to incorrect data paths anywhere between 1850 and 2034, instead of the actual recordings, which makes it possible to automate ingest. Head of Data and Digital Preservation, Stephen McConaughey, launched our R&D project to replace Redux with an open source Python alternative that we can maintain and enhance ourselves. Stephen, Joanna and myself, aided by digital capabilities engineer Brian Fattorini, began researching hardware, streaming technology and open source tooling that would allow us to successfully build a replacement. I should emphasize that although there's lots of research for such a project, a good deal of our drive and direction was provided with the need to replicate Redux with the aim of avoiding too much disruption to our ingest workflows. Excuse me. This month I'm delighted to say that we launched STORA, System for Television Off-Air Recording and Archiving. 36,000 kilometres above the equator at 28.2 degrees east is a cluster of satellites called Astra. They broadcast some 470 services, mostly direct-to-home channels to Europe. And yes, we still are in Europe geographically. The frequency range is 10.7 to 12.7 gigahertz of the Ku band as two bands. These are received by our dishes. They're a bit larger than the domestic types to add some resilience. Only one of these is actually used for STORA. At the focal point of each dish is a low noise block or LNB. We use a particular type called a Quattro LNB. This differs from domestic types on outputting 4 kinds of signal. The 4 kinds are low band horizontal, low band vertical, high band horizontal, and high band vertical. It converts these signal into a lower frequency that can be easily sent down 4 cables. Apart from polarization, many other methods are used to optimize data throughput from the satellite transponders to the receiver. And because there is so little interference in the sky, methods such as QPSK and QAM can be used. The result is that a good quality HDTV channel needs only 5 megabits per second. We chose receiver cards made by TBS TV. These have been dependable on previous projects. TBS have a range of PCI cards for satellite, cable and terrestrial reception. We use the open source drivers that are linked from their website. This TBS 6909X card has 8 receivers on it, but only 4 input connectors. Each pair of receivers shares a connector. And so they must also share band polarization and signal type. We decided to route all our satellite feeds through patch fields to make the maintenance and fault finding easier. You can see there's a multi-switch on the shelf below. We also use F-connector to BNC adapters where possible, so we can use BNC cables. Being bayonet fixing, these are much quicker to swap. A multi-switch is used to select band and polarization requested by each receiver by a standard voltage and tone system. Polarization is selected by a voltage change. Low or high band are selected by a 22 kHz tone. We use 3 receiver cards in STORA, so there's a possibility of receiving 24 different multiplexes. However, that is limited by the receiver connector sharing mentioned earlier. To record approximately 20 channel streams simultaneously to disk in a real-time system, the number of IOPS exceeds the capacity of conventional HDDs and some SSDs. We therefore went for the fastest available, NVMe. We also chose 3.5-inch form factor to allow hot swapping from the front of the server in case of drive failure. Our initial STORA system is built on an HP DL380 Gen 9 server. We configured the server to have 2 sets of RAID drives. The system drives are regular spinning drives, data drives are NVMe SSDs. To allow us to run 3.5-inch form factor NVMe SSDs, we needed an NVMe enablement kit from HP. It includes the PCI interface card, drive frame and cables. We needed a second riser card to accommodate all the PCI cards, I beg your pardon. The server must have a 2U chassis to accommodate all this, and also the receiver cards. We discovered that hardware RAID is not supported with NVMe enablement card, but Linux can create a software RAID using multiple disk and device administration resource. Each receiver card can demodulate a multiple program transport stream. We use a proprietary application built by CESPO, incidentally called Astra, to demux the TS to a single program transport stream, or streams. Here we have chosen 2 channels from the multi-program transport stream, and we use Astra to each produce program streams. We use a unicast RTP stream to record and a unicast UDP stream for event information table retrieval. The RTP stream is more robust. The UTP stream is chosen because it's compatible with Joanna's event information table retrieval software. All streams are local unicast and with individual port numbers. We did run some HLS streams for monitoring purposes during development. Astra is the only proprietary app we use. There may be open source alternatives, but we had experience with this software and the license cost just €220 a year. In fact, we use it for a backup system for Redux. We developed a backup system recording entire multi-program transport streams to disk with mux, date, time file names. These are put onto LTO tape manually. The STORA capture hardware and recording methods were developed from this old rudimentary system. In particular, we have to thank the developers of VLC who made it possible to dump a multiple program transport stream to disk. This is an example of a setup page for streams on Astra. The lower part of the page you can see the source receiver selection and the output stream setup. This is the Cespo Astra dashboard. On the left are the receivers showing frequency and signal quality. To the right are the selected channels and the data bitrate. The first STORA hardware was a development project, so we kept costs low by using a used server. It has now matured into a finished dependable system, so we are now building a second STORA with slightly higher specification and all new parts to use as our primary system. Our original STORA will be used as a backup system. I'd like to hand over to Joanna, who will describe the STORA software. It's all free from now on.
Thank you, John. Hello, I'm Joanna White, Collections and Information Developer at the British Film Institute. I'm so delighted to be here, I have to say. This is the best conference in the world. I just have to get that off my chest. So before I show you the code, I'd like to illustrate what the scripts need to achieve. I feel that's the easiest way to start. So STORA records 17 channels each day. They're a mix of high definition and standard definition streams, some broadcasting 24 hours a day, and others, such as children's television, have a shorter broadcasting time. One full day of off-air recording can capture 500 programs to file. The examples here have been prepared for ingest to our collection management system and have been numbered according to their item record number. These 500 files use up roughly 850 gigabits of storage space, so that's approximately 300 terabytes of data recorded and ingested each year. It currently takes approximately 5 days from program capture to the files to progress to our LTO tape libraries. So each recording is formatted with a date and channel path, which you can see at the top. The program folders are named with the broadcast start time, which is the unique event ID in the middle, and the duration at the end. So our highlighted program, for example, started at 9:05 AM on the 10th of October and lasted 30 minutes. All times are coordinated Universal Time, UTC, so it's 1 hour out for us. It actually aired at 10:05 in the UK. So within each of the program folders are 3 files created by the STORA scripts. First is the info.csv, which you see at the bottom. This file contains program information including channel, title, description, broadcast date, start time and duration. Next is the TS file itself. Using VLC again to play it, you can see the subtitles track in real time as text overlay. And you can check the event information table program data. It's really nicely visualized in VLC with the now and next metadata for the file itself. Finally, we also make a subtitles file which contains the extracted transcript of all spoken word from the program. This data is stored in its own subtitle stream, DVB, teletext, or one of each, making sure we don't lose any of this stream data that we've just demonstrated is critical to our preservation goal. So let's talk about the code. The code scripts can be broken into 3 groups roughly. We have schedule management, the creation and updating of EPG schedules necessary for recording some of the scripts. We have the stream recording scripts to capture the actual TS files and manage the potential failure of the recordings. And we have the ingest preparation, which sees creation of additional files required for ingest. So the schedule management scripts are responsible for downloading the electronic program guide, or EPG, you'll hear me say. And that's metadata, creating the schedules required for the recording scripts and also maintaining as up-to-date a schedule as possible by making edits in response to stream duration changes. So fetch STORA schedule is a Python script, you can see because it's got the .py on the end. Every day it fetches the EPG metadata for each of the channels for the next 4 days from the PATV metadata's REST API. Each time it runs, it checks if an existing schedule made in one of the previous 4 days is different to the new one, and it updates it if it needs to. It uses the Python requests library to call the API's URL. Did that update? No, I've skipped too far ahead. That's it. No, it did, sorry. It uses the request library on the API's URL, shown at the bottom half here. Passes the BFI's unique key as a header and requests each channel's schedule for the next 4 days. It then takes the data in its original form as a JSON file, which is shown on the left, extracts the title, start time and duration, and creates the schedule for all the day's programs as a list of dictionaries on the right. And this is the dictionary that we use in the recording scripts. Stream schedule check scripts. So these 2 scripts essentially complete the same function, and that's to check the stream data for changes to program durations when compared to the channel schedule. So where these scripts differ is how they access the program data. The example on the left shows the metadata being retrieved using media info and the TS file version. So yeah, it actually gets the data from the TS file itself. And the example on the right is using software DVBT, which is DVBT-EE, to access the event information table in the user datagram protocol, or the UDP stream that John introduced earlier. So the DVBT library relies on VLC libraries, and it doesn't work, unfortunately, with the real-time transport protocol streams, so hence we need the separate UDP stream. And here are the examples of the data that it retrieves. So the script trims each of these data blocks and accurately returns the now and next data that we need for the program start times, durations, and titles. So here's a log message for a change to BBC News HD schedule. At the top you can see a 180-minute news program that was shortened to 150 minutes, and a new 30-minute program about the escalating war in the Ukraine was added. The lower images show the BBC News HD schedule before and after the update. So the script needs to ensure schedule adjustments don't overwrite programs still due to be recorded, or don't leave any gaps in the schedule. At the moment, only Channel 4, More 4 and Film 4 use the media info method to check the event information table because their UDB data isn't very reliable. So for the same reason that we have 2 schedule updating scripts, we also have 2 different recording approaches. 14 of our 17 channels are recorded using the event information table now and next data fetched from the UDP stream, and 3 recorded using the EPG schedule recording scripts, again as we just said, Channel 4, More 4 and Film 4. We also have shell scripts that manage restart of the Python scripts should one of them fail. So, thank you. Running status recorder. This script receives a channel name passed as an argument on launch. It then uses this channel name to retrieve both UDP and RTP stream details from config files. The script uses DVPT, as we said earlier, to repeatedly download the event information table from the UDP stream to monitor the running status field. So when a new event ID appears for a program along with running status 4, then the new VLC recording launches using the RTP stream. It creates the correct folder name for the program based on the start time and the duration from the EIT data. Then it starts recording the TS file. So these logs show a new event ID being received at 8 PM and added to the current event list of a previous recorded programs. This first action is to stop the running of the VLC recording, then it initializes the new recording path and begins a new VLC recording into the folder path. And these are the shortcode functions responsible for initiating these actions. So the VLC instance being launched in the record stream function at the bottom is using the demux dump command, developed by John, actually, the command, but also helped by the Discord community, VLC community, to help me convert it into this command that we're using. So the script has no reliance on the EPG channel schedules, as we said, but I felt it's worth keeping the schedules up to date for all the channels, because if the channel 4 schedules can, data can change, then any one of them could at any time. So the other recording script, EPG channel recorder, uses the EPG schedules by loading the data and stopping based on schedule timings. So this script is launched before midnight every day, but can be reloaded at any time during the day. So that I had to create a time calc function that checked when the launch was and made sure that the date was correct for the day. The loaded schedule is converted into the script to a dictionary called recordings, and this contains the RTB address, channel name, start date, duration, end time, program name, and the RTP stream ID, or SID. So it loops continually through the recordings dictionary, looking for items that have passed their start time but have not yet finished their broadcast. So any that have passed their end time are removed from the dictionary so that there's not repeated checks. For each loop through the recording dictionary, this function checks the modification time of the schedule to see if it's changed. If a change is detected because the schedule is reloaded into the script and the recording dictionary times are updated, so that extends the recording at that moment. So the shell restart scripts, they're necessary for any script failures to any one of the channels. So this example for BBC News HD checks every minute that the Python code hasn't failed by using pgrep. Where it just looks for the name of the script and the channel. If no processes are returned, then the script relaunches the Python, at the same time puts an empty restart text file in the recording path, which is at the bottom there. And my plan is to use that date time in our SID database so that we can update viewers that there may be a slight break in the stream. Okay, for stream failures, open source software Nagios is used. So these have been created by Brian Fattorini, and they specifically monitor if a stream's video is not being written to disk. When the stream error is fixed, the scripts will immediately begin recording again. And our final line of defense, should we suffer a localized power outage in our Berkhamsted premises, is a backup system running from Gaydon, which will capture exactly what we capture with the STORA scripts. So the last few scripts, which we'll rush through, organize data so it can be ingested into our collections management system. They generate the info CSV file and the subtitles file. This is the get stream info script, which uses Python subprocess module to make a media info call to retrieve the file's TS running time metadata. The start time's compared to the program's folder start. Thank you. If it matches, the script reformats the metadata for CSV using the title, description, start time, and duration, and saves it alongside the TS file named info.csv. And the subtitles. We use CC Extractor for this, again launched from subprocess call in Python. It's quite a simple script. It identifies programs that have been completed, it checks if the subtitles already exist, if not, and then it creates it. It also outputs it to WebVTT format, which you can see here very quickly. So that's a quick look at the scripts, and here are all the open source projects that we've used to build this project. Linux and its myriad of tools, obviously, so just one symbol for that. Python, VLC, Media Info, libdvbt, FFmpeg, CC Extractor, and Nagios. We are incredibly grateful to everybody who puts time into these projects. Thank you. I also like to thank one more person, jwhite88, who posted on Active State Code 7 years ago a Python 2 script, which actually works for RTP stream recording, and this was a major influence for our script writing. And yeah, I think it's a wonderful example of how being open and sharing your code can benefit people long into the future. So in line with the conference's focus on transparency, teaching, and trust, I'm thrilled to say our code base is now open source, and you can find it on our GitHub. The repository contains all the scripts, information about dependencies, and our Linux operations environments. The last few months of UK television have suffered increasing schedule instability, with political and royal events dominating live broadcasts. It's been a really fascinating time to test STORA. We can't assume society will function according to predictable patterns anymore, certainly in the UK. And so there's never been a more important time to accurately document televised social history. So we are incredibly grateful again to the open source community for providing the wonderful tools necessary to build this code base at this very important time in history. Okay, thank you.
John and Joanna, thank you so much. This is wonderful. There is no time for questions, but your homework assignment is in the repo. We'll have an overview tomorrow, so we can ask a critical code review.